Okay, so it started recording. So let's begin. Let's begin by recalling what we did last time. So last class we introduced these Dedekind domains, which is of course very important in this course. And why is it important in this course? Because in algebraic number theory, we are going to study number fields, finite extensions of Q, and the ring of integers in those number fields, and they are Dedekind domains. So that's why we study Dedekind domains a little bit generally, because our interest is in ring of integers of a number field. So we introduced Dedekind domains. We proved that the ring of integers is indeed a Dedekind domain. We did it last time. And then we proved this very important theorem. Right, I mentioned that in Lang, not many theorems are there. I mean, mostly he doesn't call Russell's theorems. He does it rarely, and this is only theorem 2. Okay, so what did it say? It said that so we introduced fractional ideals, and it said that all the non-zero fractional ideals together they form a group, and from that we deduced that unique factorization is there for ideals. Any ideal can be written as a product of prime ideals in a unique way. Uh, so this was the theorem that we proved, and let's continue from there. So today also we will discuss some small results about Dedekind domains, and in the next lecture we will discuss discrete valuation rings. So okay, I haven't started sharing the screen. Let me start sharing the screen. And today's lecture is lecture 2. So one of you please confirm that you can see the slides.
Yes.
Okay, so let's continue with Dedekind domains, and today is 15th. So let's continue with Dedekind domains. So last time we proved this important result. We introduced Dedekind domains. So these are integral domains, commutative integral domains with unity, with three conditions: Noetherian, integrally closed, and dimension 1. Every non-zero prime ideal is maximal. And we showed that the ring of integers is a Dedekind domain when we proved this important theorem, theorem 2 in Lang, and we already recalled non-zero fractional ideals will form a group. So what is a fractional ideal? A fractional ideal is an O module in the quotient field with the property that there is some element in the ring with which when you multiply this submodule of the quotient field is actually part of your ring. So C times A is contained in O. It's actually an ideal. And then we showed that the non-zero fractional ideals will form a group. So basically we had to show, and of course it will be commutative because the ring is commutative. P1, P2 is P2, P1. So what were the important steps? So we did it in 4 steps. That this will be a group. So we had to prove that every ideal is invertible, from which it follows that every fractional ideal is invertible. And this we did in 4 steps. In the first step, we showed that every ideal contains a finite product of non-zero prime ideals. And then I guess we showed that our result we showed for maximal ideals. That was step 2. Every maximal ideal is invertible. And then from that we showed that every non-zero ideal is invertible by a fractional ideal. And we also showed that for an ideal A, the set that we defined A inverse, that is the inverse. We showed that in step 3. And the last step was to show it for any fractional ideal. And then as a corollary, we proved that you have unique factorization of ideals. So this is what we did last time. Today we will do, some small results about Dedekind domains. A word about Lang's terminology. So though sometimes I might say domain, etc. Sometimes, I'll just go with Lang and say ring. So once again, a ring stands for a commutative integral domain with unity, and a fractional ideal means a non-zero fractional ideal, and a prime ideal means a non-zero prime ideal. And sometimes we might just say a prime. I might have already used these terminologies from Lang without stressing it, but I think it's all clear from the context. Okay, so once again, I'm repeating these things. And now let's prove. You know that, I mean, the famous thing that you learn in your beginning of your algebra course, that a Euclidean domain is a PID is a UFD, and you would have done counterexamples in the other direction. So a PID is always a UFD, it's very generally true, and you would give a counterexample in the other direction. In fact, we recall last time one of those, and there are many counterexamples. But the point is, for a Dedekind domain, it is if and only if. A PID is always a UFD, but a UFD is also a PID, provided it's a Dedekind domain. Okay, so let's see that. So for a Dedekind ring, the converse is also true. Okay, so of course we will make use of what we did last time. That anything can be written as a product of prime ideal. So that's an important property of Dedekind ring. Using that, you can get many nice observations, many nice results. This is one such. A UFD is a PID. So what do you have to show? You take any ideal, call it A, and you have to show that it is principal, right? An arbitrary, any ideal is principal. It is singly generated. So we will show that this is singly generated. So take any element x in A, and first observation is that there exists an ideal B such that A times B is the ideal generated by x. So given an ideal A, and choose any x as you like from A, and then of course x is the ideal generated by x is contained in A, but we are saying that there is some ideal such that B such that x is equal to AB. Okay, that's because it's a Dedekind domain. Why is that? So indeed, what should be the answer? One of you want to say, if finally if this is true, then there's only one choice for B. What is it? What should it be? We know that fractional ideals form a group, etc. So in terms of fractional ideals, what should be the answer?
A inverse.
A inverse x. That's the obvious thing if this has to be true. So take B to be A inverse x. On first sight, this is only a fractional ideal because A inverse is a fractional ideal. But on the very next moment, you can conclude that this is in fact an ideal. Why? Because x is from A. Because x is from A by the definition of A inverse, right? What is A inverse? It is set of all x such that x times A is contained in O. So x is in A. So this is contained in O. So a fractional ideal which is actually contained inside your ring is an ideal. So B is in fact an ideal. So RHS is an ideal since x belongs to A. So this is the first observation. And now you have got this element x, right? So this x you can write as p1 power r1 etc. ps power rs, where pi's are prime elements of O. Why is this possible? Why is it true that any x can be written as a product of prime numbers, prime elements? Because it's a UFD. So you have used the fact that it's a UFD. So X has a prime factorization. So do that. So since O is a UFD. Therefore, the ideal generated by X will be what? It's easy to see that if the element is given like this, then the ideal generated by the way, a prime element will generate a prime ideal. That's obvious. So double check that. The prime ideal will generate a prime element will generate a prime ideal. So if X admits this factorization, then this ideal X has a factorization P1 power R1 etc. Where what is P1? What is this math frac P1? What should this be? This is the ideal generated by this element P1. So you obviously have this factorization where Pi is the principal prime ideal generated by Pi. Okay, so you got this, and And from this now, what can you say? So AB is equal to this product. If AB is equal to this product, what can you say about A? By the way, A will also have a factorization. And what will be the factors of A? It has to be from these things only, no? Because A times B is this product. So A will involve some of these prime ideals with some coefficients which are less than or equal to Ri. Pi will come with less than or equal to Ri. So unique factorization is there in O that we know. Therefore, it follows that A is a divisor of this ideal. So it will be of the form P1 power K1, Ps power Ks, where Ki's are less than or equal to Ri's. But doesn't matter, whatever it is, P1 is generated by P1, etc. So this ideal is generated by P1 power K1, etc. Ps power Ks. So in particular, A is principal. Okay, so it's a nice proof that a UFD, if it's a Dedekind domain, is automatically a principal domain. It's a PID. Okay. And there are many nice consequences. For example, you have cancellation. So if ABC are ideals in O such that AB equal to AC, then what should be the result? What is the meaning of cancellation? Then B equal to C. And this is true. Why is that? Because you know that there is a D. So take A. There is an ideal D such that AD equal to AD is principal. So it's generated by some X. Where from the proof last time, what do we know? X belongs to A, right? Uh, So with an x belonging to A, right? In the proof here, we proved that AB equal to x, where x belongs to A. So similarly here, you can write it as singly generated, where for some x in A. And therefore, you have AB equal to AC multiplied by D on both sides. So this will be ADB, that is XB, and this will be ADC, that is XC. So you got X, the element X times B equal to element X times C, from which it follows that B equal to C. So this is a corollary, the cancellation that you can cancel ideals. So if AB equal to AC, then B equal to C. This follows from the previous result. Okay. Fine. And last lecture, the very last slide, I said that there is uniqueness of factorization. And let me quickly recall the proof. So we had the following argument. If P1, P2, etc., P are equal to Q1, Q2, etc., Qs, then I said that P1 divides this, and therefore P1 divides this, which means P1 divides one of those, Qi. So P1 divides Qi. And so if P1 divides Qi, then Qi is P1 times something. Qi is P1 times something, and P1 times something is contained in P1. So Qi is P1 times something, therefore Qi is contained in P1. And if Qi is contained in P1 for some I, then by maximality, Qi equal to P1, because Qi's are also maximal, Pi's are also Qi is maximal and Pi's are also maximal. So Pi equal to Qi multiplied by P1 inverse and done by induction. This was the argument. This is fine. Whatever we did is correct, but I used the phrase that is. So that might say that it's if and only if, right? Qi contained in P1 implies P1 divides Qi also. Whereas the definition of P1 divides Qi, I think Manav said it correctly last time, is that Qi equal to P1 times something. So this is a consequence of that, but the other way is also true. So what I have written is not wrong, though it requires one small argument. Let's supplement that. So in a Dedekind ring, so typo, I should be small. In a Dedekind ring, A divides B if and only if A contains B, which is the obvious direction. If A divides B, then B equal to A times something. So B is contained in A. So this direction, A divides B implies A contains B is obvious. This direction is obvious. The other direction also is not difficult, because conversely, if A contains B, then from what we have shown, there is some ideal C such that AC equal to AC is the principal ideal. So take some C such that AC is principal where X belongs to A. But if AC is generated by X, I can take 1 by, so I'm going to take 1 by X AC. So what if this is true, what can you say about 1 by X AC? What can you say about 1 by X AC? If AC is generated by X, that means X times O. What can you say about 1 by X AC? So I'm not coming here. Here itself I am asking you. What is 1 by X AC? What will it be?
Student.
Say that again.
So what did you ask? 1 by X into AC.
Into AC, yeah. X is an element, non-zero element. So take 1 by X.
Entire ring, right?
Hmm?
That would be the entire ring, right?
That will be the entire ring. Yeah, correct. So 1 by X AC will be the full ring. And I'm taking 1 by X, not AC. I'm taking 1 by X BC. Okay, B is contained in A. But if 1 by X AC is the full ring, then 1 by X BC is contained in the full ring because B is contained in A. So this is indeed an ideal. So the point to note is because of this, D is a proper ideal. Okay, D is a proper ideal. What do we need to show? We need to show that B equal to A times something. And I give you D to be this. And what is AD now? What will be A times D? It will be 1 by X ABC. So that is B times AC. But B times AC is X. And X goes. So this is B. So if you multiply this with D, you do get B. So note that AD equal to B. So you have shown the other way. If A contains B, because you are in a Dedekind ring, you have this property, and using that you could give a D such that A times D equal to B, showing that A divides B. So this will be the definition of A divides B. There is something so that B equal to A times that. So the only reason I recalled us this writing that is needed a small explanation which we have done here. But we are not using that there. We used only the obvious direction. Okay, so I'm not changing last lecture slides because the direction that we have used is obvious, but the other direction is also true, and here is a proof. Okay, here is another result. I have written it as finiteness implies PID, but finiteness of what? So the result is that suppose your Dedekind domain has only finitely many prime ideals, then it's a PID. Is the statement clear? If your Dedekind domain has only finitely many prime ideals, then it is a PID. And the proof again is a corollary to our yesterday's result. So let's do that. So there are only finitely many prime ideals. So enumerate them, call them P1, etc. PS. So this is these are all the prime ideals that you have. Are all the prime ideals of O. And now what do we need to show? We need to show that any ideal is singly generated. So take an ideal. So let A be any ideal. You have to show that A equal to A is generated by one element. That's what we need to show. But what do you know about A? A can be written as a product of primes, right? We have shown yesterday that any ideal is a product of primes. So we need to show this is principle, but you can start by writing A equal to, these are all the prime ideals. There's no other prime. There is finiteness. Therefore, this has to be P1 power R1, etc. PS power RS, where some RIs may be zero. I don't know. I don't care. Some primes may not come, may come, whatever. A equal to P1 power R1, etc. PS power RS, where RIs could be zero or positive or zero, non-negative. Okay. So this you have. Now the proof uses Chinese remainder theorem. So what we are going to do is, first of all, let's take elements which belong to the prime ideal Pi but not in its square. So take Pi from Pi minus Pi square, Pi minus Pi square, and PIs are mutually comaximal, right? So sometimes, I might have used earlier comaximal and coprime interchangeably, which perhaps is not quite true, is it? Or it is interchangeable. So in your algebra class, if you have ideals I and j such that I plus j equal to the full ring, do you say I and j are co-maximal or co-prime?
Co-maximal.
And what is the meaning of co-prime then?
I don't know what is the meaning.
Oh, there is nothing called co-prime? Okay. Then maybe
Maybe
it
there
is.
is, but I'm not aware. Like I think.
Okay. So my feeling is maybe, so I forgot to double check. You please double check and let me know. I will also, if I remember, I will also do that. I have seen the word coprime, so I think it means this only, comaximal. Okay. Anyway, whenever I use coprime, I had in mind comaximal only. Somehow I always use coprime, but then I did not double check the terminology. But I have started seeing comaximal. But whenever I use coprime, even if there's some other meaning of coprime, that's not what I had in mind. We used it only for Chinese remainder theorem, and it's comaximal that I had in mind. So PIs are mutually comaximal. Why? We have used this many times because PIs are maximal. So P1 plus P2 has to be the full ring for any indices I and j. Pi plus Pj is full ring. But from this you can conclude that, do you agree that Pi power m and Pj power n, they are also comaximal?
Yes.
If, yeah, and this is something which is not difficult, no? What is the key idea?
I think like you just take the two elements in P or P1 and P2 and
Yeah,
just A plus B equal to 1, take power K on both sides.
yeah. So you will take a sufficiently higher power, right? High power, right?
Yes.
Yeah. So binomial theorem. And x plus y power something, apply binomial theorem, and it will be in one of this. So that's true. So pi power di are also comaximal, and we are going to, for any di, we are going to use Chinese remainder theorem for certain powers very nicely. It depends on this ri. So I'm going to apply it to ri plus 1. So by Chinese remainder theorem, you can choose an x which is congruent to pi I power ri, but I am applying it to the ideals pi power ri plus 1. Okay, this is the main point. If ri is the power coming here, I am applying it to ri plus 1. Also note, suppose r1 is 0. Even then it's okay because I'm taking plus 1 here. So these are proper maximal ideals. Okay, so even our Ri being 0 is fine for this step, and Ri could be 0, we don't know. So anyway, so we have taken a common x which is congruent to pi I power Ri mod pi power Ri plus 1 for all I together. Okay, simultaneously we have chosen this x. Now the next step is you can take the ideal generated by x. You want to take a guess by now? What should be my answer? I want to show that A is principal. You want to venture a guess? I will show A to be generated by which element now? I'm not asking for a proof. I'm just asking
X,
you to take a good
X,
guess.
X,
Yeah. Say
X,
that again.
X, X.
X. Yeah. A should be generated by X. The way the proof is going, that should be true. So we have to show that. The claim is that A is generated by this X given to you by Chinese remainder theorem. Okay. So you want to also take a guess how the proof should go? You take the ideal generated by X and show that it is equal to A. So you have to take the ideal generated by X. But we are in a Dedekind domain. So what will you do? Take the ideal generated by X and do what? Any ideal is a product of primes, right? So write the prime factorization for that ideal. What will that be? It will also involve only P1, etc. PS because these are all the primes. There's no other prime. Okay, so yeah. So one small thing is that uh, yeah, this X belongs to A. Yes, so this I needed to show because, yeah, so when I asked you to take this guess, X in O says that that is correct, your guess is correct. I will take the ideal generated by X, but let's also note that X actually belongs to A. Okay, so only then bracket X can give you A. So X belongs to A because from this it follows that so X minus pi I power Ri is in pi power ri plus 1, but pi power ri plus 1 is contained in pi power ri. So x minus pi I power ri is in pi power ri, and pi I power ri is also in pi power ri because pi I is in pi. Therefore, x belongs to pi power ri, and this is true for each I. Therefore, x belongs to the intersection of pi power ri. But intersection of pi power ri is nothing but the product of pi power ri because they are all co-maximal, and that is A. So x belongs to A. Okay. And now the claim is, as you suggested, the ideal generated by x is equal to A. For that, you take the ideal generated by x and write it as product of primes. So now, I have written it as, okay, typo P1 it is. So earlier capital I and now P1, two typos. So P1 power E1, etc., PS power ES. What can you say about the coefficients EI? You want to compare. So the proof will be over if you show that EI equal to RI, right? So we are done if we can show that EI equal to RI. But one way is obvious. EI bigger than RI or EI less than RI? Which is obvious? So this is contained in A, right? Because x belongs to A, the ideal generated by x is contained in A. So P1 power E1 dot 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 is contained in P1 power R1 dot dot dot. So what can you say about E1 and R1, EI and RI? Yeah, one of you can tell me.
So like we know that x doesn't belong to pi, right?
X belongs to?
X does not belong to pi, right? You know that.
Do we need that? No, X. I haven't said anything. I have just chosen X like this. X belongs to A. That's all that I have said. But what I'm saying is the ideal generated by X is certainly contained in A, no, because X belongs to A.
Yeah.
So P1 power E1, etc., PS power ES is contained in P1 power R1, etc., PS power RS.
Yeah. So they should be greater E1.
Therefore, EI will be greater than or equal to RI. So this is obvious. What is our claim? Our claim is it is equal. And can you see where equality will come from? Equality should come from this choice of pi I. Pi I is chosen from pi but not in pi square. So because of this careful choice of pi I, we are going to claim that it's actually equal, because if there is an I such that EI is greater than or equal to RI plus 1, then x belongs to pi power RI plus 1, right? Because x belongs to pi power EI, and therefore x will belong to pi power ri plus 1 because ei is bigger than or equal to this. But if x belongs to pi power ri plus 1, then what is the property of x? X is pi I power ri mod pi power ri plus 1. So if x belongs to pi power ri plus 1, then pi I power ri will belong to pi power ri plus 1. So if x belongs to pi power ri plus 1, then pi I power ri will belong to pi power ri plus 1. That will mean that pi I should belong to pi square. But that's a contradiction because pi I was chosen outside pi square. Okay, so pi I is in pi but not in pi square. So pi I power ri can only be in pi power ri, not in a smaller ideal. So that shows that ei equal to ri for all I. So EI equal to RI, therefore the ideal generated by X equal to the ideal A. So the chosen ideal A is principal. So every ideal is principal. So if there are only finitely many prime ideals, then it's a PID. Okay. So that's another nice result. Now let's this is also something very basic. So localization with respect to an arbitrary multiplicative set. Uh, So first of all, you know this, right? Localization preserves the ring being Noetherian, no? If a ring A is Noetherian and S is some multiplicative set, then S inverse A is also Noetherian. Can one of you tell me why?
All the ideals of S inverse A, they come from A, right?
Correct. So that's the first observation. An ideal of A, ideal of S inverse A comes from an ideal of A. So if you take an ideal in S inverse A, if you take an ideal in S inverse A, then that is equal to A equal to S inverse of A intersection A. So, and every ideal of A is finitely generated. So this will have finitely many elements generating, and therefore clearly this also has finitely many elements generating. So localization preserves being Noetherian. It also preserves being integrally closed, which I had asked you to do as an exercise at some point. I hope you must have done it. Anyway, it's very easy. That also is easy because you take x from the quotient field of S inverse A. By the way, quotient field of S inverse A is same as quotient field of A. And if you take x from there and suppose x is integral over S inverse A, so x satisfies a monic polynomial with coefficients from S inverse A. And now you have to show that x belongs to S inverse A. Okay. But now what you do is you clear the denominators, take the product of all the si's, let us call it s, and multiply by s power n throughout. So you will get sx whole power n, s power n minus 1 times s, etc. s power n something. You will get this. And this shows that sx is integral over. Now you look at the coefficient. Where is the coefficient? New coefficient is where? an minus 1 by sn minus 1 and s. S is the product of si, so sn minus 1 cancels. So all these coefficients now are in the ring A. Right? These coefficients were in S inverse A, but because you have cleared the denominators, these coefficients are in A. And that means Sx is integral over Sx is integral over A, but A is integrally closed. We want to prove that if A is integrally closed, then S inverse A is integrally closed. But A is integrally closed, therefore Sx belongs to A. So Sx is in A. If Sx is in A, then X is of course in S inverse A. So localization preserves being integrally closed. And localization, what happens to the dimension of A if you localize? How do you compare dimension of A and dimension of S inverse A? Dimension of S inverse A is at most dimension of A. Do you see that? Because if you have a chain P1 contained in P2 contained in P3 contained in etc., then you get S inverse P1 contained in S inverse P2 contained in etc. There could be some equality while doing this. So it could go down, but it cannot go up. So it decreases the Krull dimension. Therefore, if you take a Dedekind domain and if you localize, what will happen? Noetherianness is preserved, integrally closed is preserved. If you took a Dedekind domain, then the Krull dimension is 1. By the way, strictly speaking, I should not have said Krull dimension equal to 1. What should I have said? I should have perhaps said, anyway, what is of interest to us is integral Dedekind domains with Krull dimension equal to 1. Maybe I should have said Krull dimension, so this might vary from book to book. Maybe I should have said Krull dimension less than or equal to 1. What is dimension 0?
Field.
It's a field. So, you know, according to some people, maybe a field is also a Dedekind domain. Okay, so decreases the Krull dimension. So if you started with something with dimension 1, you may get dimension 0 or 1. So if you include fields also as Dedekind domains, then localization of a Dedekind domain is a Dedekind domain. Okay, so being a Dedekind domain is preserved under any localization for any multiplicative set. And one more observation is that if you have two ideals A and B, and what will be S inverse of the product of AB? So an element here will be something in AB by S, and something in AB will be summation xi yi. So it is of the form summation xi yi by S. That's of the form summation xi by S times yi or whatever. So whichever way you can take. So this is equal to S inverse A times S inverse B. Yeah, so this is easy. So it's clear that this is contained in this, and if you take something here, again it's obvious that it belongs here. So S inverse of AB is S inverse of A times S inverse of B, that's obvious. Therefore, you can conclude that from the group of, so if you have a ring A, that's a Dedekind domain, suppose, then we just proved that the localization is also a Dedekind domain. So you have a Dedekind domain on the left, you have a Dedekind domain on the right. And you have the group of fractional ideals on the left, you have the group of fractional ideals on the right. And we just showed that this map is a homomorphism from this group to that group. So A going to S inverse A is a homomorphism from the group of non-zero fractional ideals of A to the group of non-zero fractional ideals of S inverse A. Okay. First question, what is the kernel of this map? Can one of you tell me? So what is kernel by definition? Set of all A such that S inverse A is the unit element. What is the unit element? S inverse capital A. So it is set of all small a such that S inverse A equal to S inverse capital A. S inverse small a equal to S inverse capital A. So what is the property of A? Is there a kernel or kernel is zero? Maybe you can take a pen and paper and quickly do it. What's a kernel? Yeah, Manav, you're telling me something?
Oh, my mic is on. No, I'm trying to talk.
Okay, okay. Do it. All of you do it. Yeah.
We need to use that A as a factor ideal.
Once again.
We need to use that small a is a fractional ideal.
Yeah, yeah, A is a fractional ideal. That is given to you. This map is from the group of non-zero fractional ideals to the group of non-zero fractional ideals. So what you want to compute is set of all A such that S inverse A equal to S inverse capital A. The only thing that you need to show you use the fact is that the full ring contains 1, right? So if S inverse A equal to S inverse capital A, then 1 belongs to S inverse A. S inverse small a. 1 belongs to S inverse small a. What is the meaning of 1 belongs there? An element in S inverse A is of the form A by S. And A by S equal to 1 means what? A equal to S. What does that mean? There is an element in the multiplicative set which intersects your IB.
A by S equal to 1 doesn't mean A equal to S.
A by S equal to 1 meaning A equal to S only, no?
No, A by S equal to, like, there's a in localization it's different. A by S equal to 1 means that S prime A is equal to S prime S for some S prime A belonging to capital A.
No, suppose 1 belongs
It's a domain, oh yeah, it's a domain.
It's a domain, yeah. S is just a multiplicative set, and by definition, it's some A by S only. There's no equivalence or anything. We are in a domain. Okay. So the kernel, your computation shows that the kernel is precisely those fractional ideals which meet S, meaning which intersect S, your multiplicative set. So kernel is those ideals which intersect S. And next question is this map surjective? A going to S inverse A, is this map surjective? Is it onto? This you have already answered. Manav had answered it in the previous slide. right? When I asked this question here, you said that any ideal is coming from the ideal there, right? Any ideal is of the form S inverse of A intersection A. But if this is true for ideals, this is true for fractional ideals also.
Yes.
So it is surjective. So you've got a surjective morphism from the group of fractional ideals of A to the group of fractional ideals of the localization, whose kernel is easy to describe. It is exactly those ideals which intersect with those fractional ideals which intersect your multiplicative set. Okay, so keep that in mind. I haven't put the answers here. These are obvious. Kernel is that and surjective answer is yes. Okay, now we will stop after this. So we are stopping a bit earlier today. But class group I have introduced in the last class verbally. Can one of you recall what the definition is? Class group. Some people will call it the ideal class group. Let's just call it class group. What is the definition? I think I said it verbally. It was not part of my slides.
I don't remember at all.
You just said it or you said you don't remember? See, I'm not hearing properly.
Can you hear me now?
Ah, yes, yes, yeah.
No, I don't remember the definition.
Okay, okay. So anyone else? This was Manav. So this is the thing. When I'm on the other screen, I don't know who's speaking because Manav is frequently telling me I kind of recognize his voice. So this was Manav, I guess. Anyone else? Amanpreet, do you remember Amanpreet?
No, sir.
No. Were you there in the last class?
No, sir.
Okay, Pradyumna, do you remember?
No, sir, don't recall.
Again, you have to speak louder, Pradyumna. I can't hear you.
Don't recall, sir.
Don't recall. But do you recall that we mentioned class group?
Yes.
Okay. So let's try to recall what could it be. I said, this is one of the important, perhaps the most important theorem from the course. Do you recall the theorem? Forget what the definition is. I said there's an important, this is perhaps the most important theorem of this course. And I said, hopefully we can do it. By the way, this group of, okay, do you have one group in front of you? At least tell me that. From whatever we have done yesterday, there was a group, no? What is that group? Group of? It's a Dedekind domain. What was our theorem?
Fractionally
Yeah.
ideal.
So fractional and non-zero fractional ideals form a group. So you certainly have that group. So you could have said as a guess that that is the class group. That will be the first guess, which is not quite correct. And this group contains, by the way, is this group abelian? Group of fractional ideals. What is a product? If you have A and B, product is product AB. Is that abelian?
Yes.
Yes, because why is AB equal to BA?
Domain
The ring is
commutative.
abelian.
Your ring is commutative. So something in AB will be of the form summation xi yi, but that is equal to summation yi xi. So the ring is commutative. So AB is BA. So this is an abelian group. And you take the following subgroup, which is the group of all non-zero fractional ideals which are principal, meaning generated by a single element. So that will be a subgroup. Is that a normal subgroup? Yes, because the full group is abelian. You take this quotient. This is the definition of the class group. Okay, so its class group is defined as the group of non-zero fractional ideals modulo the subgroup of non-zero principal fractional ideals. And any subgroup is normal because of abelianness. Okay, so very, very important definition. This is the class group. And it's abelian, so it's fine. So this is the class group. Okay, a group of fractional ideals divided by the group of principal fractional ideals. Now, do you remember the theorem? Theorem is about the class group, and take a guess or say something randomly. Doesn't matter.
Our group is normal.
Class group is
Normal.
normal way. It is one group.
It's
So
a normal. Oh yeah. Normal subgroup of.
There's nothing else there, so it can't be normal because I have given you just one group G, and it's a property of that group G that we are is a theorem. It's one of the simplest properties. So if I give you a group G, what is the first question that you can ask? That is the answer.
Is it
Normality and
abelian?
later.
Is it abelian? That's the first question, right?
Abelian answer is yes, because it's a quotient of an
Yes.
abelian group.
Yeah.
So that would not be a big theorem because that's obvious. But if I suppose I give you a group G, okay, even before abelian, there is one thing that you will ask, or you should have. Suppose I
Fi-
give you capital G a group, nothing else is given to you. What will be the first question?
Finite or not?
Finite or
Cyclic.
finite or not? Before coming into anything as a set, is it finite or not? And the big theorem of the course is this class group is finite, not for any Dedekind domain, but for the ring of integers of a number field. Okay, algebraic number theory. So this is what is of interest to us. K is a number field and take OK. OK is a Dedekind domain, ring of integers, and its class group. Definition is thus, and this is finite. This is the biggest theorem of this course. In fact, much later, I mean, whatever you do, if someone asks you, I mean, if you tell someone you had a course in algebraic number theory, and if someone asks you to remember something, this is all that you need to remember to show that you had a course in algebraic number theory. The class group is finite. Okay, there's one more important result, which also we might do called the Dirichlet unit theorem. We will see, but this is the most important theorem. And the order of this group, it's finite, and therefore the next natural question is what is that number, right? If you have a finite set, of course you would like to know what that finite number is, and that is called the class number of K, or class number of OK, class number of K, let us say. Okay, is the definition absolutely clear? So this theorem will take some time. We will do it towards the end of the course maybe. But there are two questions that I can ask you right now, and you should be able to answer if the definition is clear. Okay, first question. Okay, before that, let me tell you one more thing. What is the meaning of class number 1? This group is trivial, no? This group is just the identity, right?
Yes.
Group is of order 1. What is the meaning of that in terms of the group?
Every
All
fraction.
fractional ideas are principal.
Every fractional ideal is principal. So what can you say about that ring?
PID.
It's a PID. So class number 1, if and only if it's a PID, and we are in Dedekind domains. Therefore, PID if and only if we just did it a few slides ago. UFD.
UFD.
So class number 1 is a characterization of unique factorization. And I told you last time, right, when I was doing this, I said no, there's a history related to Fermat's last theorem. Those interested can Google, etc. And the keyword is Kummer when you want to Google. So you can check. If your ring of integers, if all the rings of integers were UFDs, then there was a way to attack Fermat's last theorem. This is how people started studying, and then you realized, not everything is a UFD, but you can get unique factorization at the level of IDs. So not everything is UFD, same as saying not every class number is 1. Okay, class number can be bigger than. But class number 1 is a characterization of UFD for Dedekind domains. Now, can you give me an example of a number field of class number 1? This you should be able to do. Just one example.
Z.
Yeah, so number field, so Q, right? Q has a ring of integers Z, and Z is a PID. So that you have answered. Q has class number 1. Now, can you give an example of a number field of class number strictly bigger than 1?
Example of a number field which is not a UFD.
Correct. So give me that. This was there in the last class, no? In fact, this is
That
Root
long
5.
z of 1 plus root minus 19 by 2. That won't be a PID.
That will not work, no, because that will be a Euclidean domain as what that's not that was an example of a PID which is not a Euclidean domain, no?
Z root 5i.
Yeah, the other one, the easier one. So Q root minus 5, right? That's where you said 2 times 3 is 6. which can also be written as 1 plus root minus 5 times 1 minus root minus 5. And I asked you to verify, or you must have verified in your algebra class, otherwise verify that these are all these are two different, and these are all irreducible. So all these four elements, 2, 3, 1 plus root minus 5, 1 minus root minus 5, all these are irreducible. So you needed to verify that. And then this is not unique. No, so you have factorized it in two different ways. So it's not a UFD. So that's an example. So in fact, okay, you want to take a guess? What is the class number there?
2.
Yeah, answer is 2. But of course, we haven't shown that, or maybe we can't easily show that. But answer is 2. So that is an example of class number 2. Okay, so this is class number. We will come back to it later. Okay. So we will just end with one observation, which is that suppose A is any Dedekind ring with finite class group. For example, ring of integers. If you assume this big theorem, ring of integers will satisfy, but this is a general result. Suppose you have finite class group, and suppose these are the representative fractions. You fix a set of representatives, and the set of representatives will be finite, no, in fractional ideals by non-zero fractional ideals. So these are the representative fractional ideals. From each coset you take one, and that will be finite by your assumption. And take a B from your Dedekind domain such that B belongs to this finite intersection. B belongs to intersection AI. B belongs to each one of this. And take this multiplicative set, 1B, B square, etc. Right? In your algebra, there are two famous multiplicative sets. No? One is you take a prime ideal and take its complement, and this is the other famous multiplicative set, right? Multiplicative set generated by one element. So take such a B and form this multiplicative set. Now you have this homomorphism A going to S inverse A from the domain A to the domain S inverse A, and each AI is mapped to the unit ideal S inverse A. Why? Each of these AIs will go to the unit ideal. It is in the kernel. Each AI is in the kernel of this map. Why? Because earlier you
It
compute.
belongs to all of them.
Yeah, the kernel is precisely those things which intersect S, and by choice, each of the AIs intersect S because B is from this intersection. So each of this is mapped to the unit ideal S inverse A. Now, any ideal of A, what can you say about any ideal of A? It will be one of this times the principal ideal. Agree? Because these are the representatives, these are the coset representatives of the class group. So any ideal is AI times the principal fractional ideal, and under this homomorphism, where will this go? AI times the principal fractional ideal will go to the image of AI times the image of the principal ideal. But image of AI is what? The full ring. And image of a principal ideal is a principal ideal. So the conclusion is any ideal is principal. Any ideal of S inverse A is principal. So I don't quite remember now whether we are going to use this somewhere or not. Maybe this will find a application. So I don't quite remember. Okay, but very interesting result nevertheless. Under finiteness of class group, if you take this particular multiplicative set and if you localize with respect to that, then that is a PID. So here is a way to generate PIDs by localizing. Okay, right? This means it's a PID, right? Every ideal is principal. So you can manufacture PID by this construction. Under finiteness of class group, choose something from the intersection, fix any representatives, take something from the intersection, and consider this multiplicative set. And then these by construction go to the unit element, and therefore every ideal is principal because it's surjective, right? Because it's surjective, any ideal here has to come from some such thing, and therefore every ideal is principal. So every ideal is principal because of the surjectivity of this map. Okay, so let's stop there, and we can discuss for some time and then stop. So I can stop the recording because the lecture part is over. So let me stop recording. Let me stop sharing the screen. I'll stop sharing the screen and let me stop recording.